Good afternoon. We probably should get started since this seminar is going to be webcast. So we want to make sure that the people online will be able to see us. We are very pleased to have Professor Gary Lackmann to be our seminar speaker today. He came to visit the DTC, and Professor Lackmann is a professor at the Department of Marine, Earth, and Atmospheric Science of North Carolina State University. He got his PhD in 1995 from SUNY Albany. His primary research interest is synaptic dynamic meteorology. In recent years, he has extended his work toward the weather-climate intersection, specifically the relations between weather extremes such as tropical cyclones, heavy rainfall to climate change. And he and his group has also studied the dynamic and impact of tropical cyclones, organized convection, winter storm, and topographically forced flows. And Dr. Gary Lackmann has also been serving as a Unidata governing committee for 10 years, from 2003 to 2012. And since 2009, he has been serving as a member of NCAR committee, a community advisory committee for NCAP called UCAN. And today, Dr. Lackmann will be speaking with us on using the WRF model to investigate climate change influence on the track and intensity of Hurricane Sandy.
Okay, thanks. Let's see, Bill, do you want this? No? All right. Well, thanks for that introduction, and thanks to all of you. I see lots of familiar faces. It's great to come to NCAR. I feel like walking around the halls, I feel like I'm in the Atmospheric Sciences Hall of Fame, and so it's very, very humbling, but great to see so many top-notch people. And I'll have to confess that you noticed that the title that Bill read off is not the same as what's on the slide, because originally I thought this was sort of a DTC-centric seminar. I didn't realize it was kind of the whole ball of wax. So I expanded the scope after I learned that it was a broader target audience. But I'll be talking a little bit about a topic that I know some of you in this room have studied, Hurricane Sandy, and the topic of climate change, which comes up a lot in that context. I'll get into that. But so it's sort of a two-part talk. The first part is really just some broad overview on some work that I had done previously and other people have done on hurricanes and climate change. And then the second part is really specific to Hurricane Sandy. So to start off, for context, whether you trust the details of GCMs or not, if you average the large-scale conditions over decades and many GCMs, there's very robust temperature change signals that come out, and these come out of the CMIP3 or the more recent CMIP5 GCMs. And so this cross-section of temperature change, it's for the month of October, the 2090s minus the 1990s, and this is the South Pole, here's the North Pole, and this is up to 10 millibars, so you're up well into the stratosphere. We see strong cooling in the stratosphere just due to the CO2 increase. That's there's a reduction in the upwelling infrared and increase in the radiative emissions. So you get cooling in the stratosphere, and you get very strong warming in the tropical upper troposphere, which of course has implications for tropical cyclones. And then if you look carefully here over the North Pole, there's very strong warming at very high latitudes, polar amplification, which is quite shallow. These are well-known signals that are robust across models and so forth. In terms of the meridional temperature gradient, so if we just plot down here, so now the domain has changed. Now here's the equator and here's the North Pole, so we've sort of taken the right side of this. And the shading, the blue shading is where it's colder to the north, dt/dy is negative, and the warm colors are where the temperature gradient reverses above the jet core. So the jet core is right in here from thermal wind balance. That just shows the 1990s October average. But what we really care about is what is the change in the meridional temperature gradient, because that will tell us how the jet stream will change. So up here now, with this same kind of cross-section, is the change in meridional temperature gradient. And what you see is, of course, polar amplification weakens the meridional gradient kind of at the edge of the Arctic front. But across the fairly deep, and I should have picked a different contour interval to show this better, but across fairly deep areas of the upper troposphere, there's actually an increase in the equator to pole temperature gradient, and that's why the jet stream strengthens with climate warming. And so in this layer sort of between 200 and 300 millibars, you actually, because of this bulge in the warming in the upper troposphere in the tropics, thermal wind actually gives you a stronger jet. So that's often what we see, which also has implications for hurricanes, because that could mean more progressive Rossby wave patterns, more vertical wind shear, other implications that we'll get into later. So those are just very robust signals from averaging together decades of data from several GCMs. So in terms of climate change and tropical cyclones, here's a list of some favorable aspects. You get warming sea surface temperatures. If you just take Kerry Emanuel's maximum potential intensity Fortran code from his website, and you calculate the change in maximum potential intensity that you get using the change fields applied from GCMs, you mostly find an increase in the North Atlantic basin. So you see maybe 5 to 20 millibars increase in intensity, meaning that the minimum central pressure in a hurricane that reaches its maximum intensity would be that much lower. We know that with warming, you get increase in the vapor content, which means stronger condensational heating. That could also contribute to stronger tropical cyclones. And even though there's stabilization of the lapse rate, the fact that you're adding most of that additional water vapor at low levels means you increase the convective available potential energy, which means you could get stronger vertical motions. Now, on the other side of the coin, there's a number of things that are unfavorable for tropical cyclones in climate warming. That includes, with that warming in the tropical upper troposphere, you stabilize the lapse rate, you increase the convective inhibition. Several studies have shown a weakening of the tropical circulation, reduced upward motion, and in some basins, there's been some studies that have found an increase in the vertical wind shear. Some of those have, I think, are controversial, but the one that I want to focus on the most is that if the relative humidity is constant and you warm the air, you increase the saturation deficit. And a number of studies, Emanuel, going back to the 80s and 90s, but more recently Emanuel 2008 and Rappin et al. 2010, have found that that's related to tropical cyclogenesis. So, there's offsetting effects here, and this makes for a good scientific problem because you've got a list of things that get better and a list of things that get worse, and you need numerical models to help sort out which effects dominate. So just a quick summary of some previous work that I did with my former grad student, Kevin Hill. One of the things that we did is we took the Jordan 1958 Atlantic tropical mean sounding. We stuck that into WRF, ran in idealized mode with no land, constant sea surface temperature, no shear, and we just let the model run until we reached maximum intensity. And we did that with a number of different grid spacings and a number of different physics parameterizations. But what we found was actually the steady state hurricane that spun up was pretty close to what the Emanuel MPI would predict. So we were very pleased with that. And then what we did is we took the average tropical GCM change and we tacked that on and reran those same idealized experiments to see how things changed. We looked at the precipitation and the intensity, and then a later experiment we looked at the frequency, or the kind of the cyclogenesis problem. But so this paper that came out in 2011 has the details of all this if anyone's interested. But what you get if you just take the tropical, depending on which emission scenario, this is older, so it's the AR4, but the green line is the A2 emission scenario, which is kind of the most pessimistic. and the B1, the blue line, is the most optimistic, but they all show this bulge of warming in the tropical upper troposphere, which is kind of a moist adiabatic thing. If you're adding heat and moisture near the surface and there's convective mixing, by the time you get into the upper troposphere, it's all been realized as sensible heating because all the vapor is condensed out. So you apply these profiles and you run the model, and what you find is the storms get stronger. And the calculated maximum potential intensity increase, depending on which scenario you use, is ranging from maybe 7 to 11%. But WRF gives you something more than that, maybe 11 to 19%. This was with 2 kilometer grid spacing. And so, it's, you don't have to haggle about the down to the percentage point, but the point is it gets more favorable and you get stronger storms in the future. We also get heavier rain, but the increase in precip is really in the eye wall, not as much at outer radius. So you're getting the heaviest precipitation where it's already coming down most heavily. One other thing I should have mentioned about this is if you calculate the standard deviation between the climate, so we use 20 different GCMs to get these profiles, and if you calculate the standard deviation, it's largest up here. So there's a lot of variation in the strength of that bulge in the warming aloft, which turns out to be really important, because what we found is that if you just use the GCMs that didn't give you as much upper tropospheric warming, then you got a huge increase in intensity, like 870 millibar type central pressure. But if you use the GCM that gave you the most stabilization, then you barely got any increase over the current maximum intensity. So, what controls that is probably the GCM's convective parameterizations, to some extent how they handle ozone recovery and other things like that. But there's a lot of sensitivity to that. But the fact that it rained harder tells us why the storms got stronger, because if you look at the potential vorticity, this is azimuthal average over some time, PV cross sections from the sea surface up to 8 kilometers. In the current climate, this is what it looked like. With warming, you got a pretty substantial increase in the potential vorticity tower because you've got more condensational heating. And so that was the effect that really dominated and was really driving the intensity increase. But of course, the lapse rate stabilization is working against that. So we should be thankful. There is, of course, a discrepancy between the observations and the GCMs with that tropical upper tropospheric warming, because the OBS don't show it as much as the models say we should. And there's been a lot of studies, a lot of observational studies have looked into that problem. But now, so that was the intensity part. What about the frequency part? So there's this technique that dates back to the mid-1990s. The European groups at ETH and others had this idea that you could take today's synoptic pattern and apply GCM-based warming to say, well, if that same pattern happened at a different time, how would it change? How would the thermodynamics alter the event? And this is what's called a pseudo-global warming. A number of groups in Japan have used this technique. So you take, you take the ECMWF, if you will, or the GFS or the NAM or your favorite initial conditions, and you run your WRF simulation. Then you go and you take the GCM changes and apply them to that same initial condition. So here's your GCM. You tack those changes on and run the event again and say, well, how did this large-scale warming and moistening and the changes that come about, how does that change the synoptic evolution? So it's a limited approach. It's a very simple approach because it doesn't allow you to answer the question of, well, how would the frequency of that type of synoptic pattern change? But it does allow you to say, well, just thermodynamically, what do you get from that change? And so we did this computationally very expensive project. My other former student, Megan Mallard, did this where we ran with a 6-kilometer grid length over the whole Atlantic basin. And I won't get into the details. There's papers if you're interested. But this is an example showing the first 3 weeks of one of our monthly simulations at 6 kilometers. So we had a really good computer that we were able to use to run these. But this is just showing the simulated radar. And sea level pressure, you probably can't see that very well from the back, but there's some tropical cyclone activity. Then we apply the GCM changes from the A1B scenario, and you run it again. We warm the sea surface temperature, keep the relative humidity constant. Everything is exactly the same. The lateral boundary conditions are the same, except with the large-scale warming applied. And if you do that, you find that you get a lot less hurricane activity. In fact, the ACE goes way down. And this is not something that just we found. This is something that everyone, not everyone, a lot of studies have found. There's a few studies that find an increase, but if you look at like the Knudsen et al. 2010 review article, 9 out of 9 studies looking at frequency found a decrease. So it's a pretty robust finding. But the beauty of this experiment, even though it has its limitations, and you can criticize it, but the beauty is that because you're looking at the exact same synoptic pattern, we can calculate these disturbances and look at them in the current and in the future and say, well, here's one that developed in the current climate that fizzled in the future, and you can pick it apart and find out, well, what happened? Because there's a list of culprits that it could be. And so if you kind of take this zoomed-in look, here's the current climate. There's this easterly wave that came off of Africa. You see it up here. It's kind of struggling, but you can see a circulation developing. Convection wraps around it, and you start getting cyclogenesis. But if you look at that same easterly wave coming into a very similar synoptic environment down here, it's coming in. It looks like it's going to get its act together, and then it fizzles out, and it dies. And so, we looked through, we calculated the wind shear. There's all kinds of interesting problems. Nolan and Rappin and others have found that, well, when it warms and you increase the freezing level, you stretch the PV tower in the vertical, so a storm would be more susceptible to the same amount of shear. There's studies of a number of different culprits, but the one that we found that seemed to matter the most was related to this incubation parameter, which is really related to this mid-level saturation deficit. So Emanuel et al. And Rappin et al. Have this parameter chi sub m, which is basically related to the mid-level saturation deficit divided by the air-sea disequilibrium. So this denominator here is basically the difference between the saturation entropy at the sea surface and the near-surface entropy. And then up here, it's related to kind of the environmental versus the updraft entropy. So the mid-level saturation deficit. And so we calculated that, and then it makes it really clear. So here's our disturbance trying to get going, and the shaded quantity here is this mid-level saturation deficit. And you can see it's doing battle with the dry air, but the convection just can't moisten the environment enough. And that's really what controls when cyclogenesis happens, is you have to reach a nearly saturated condition for tropical cyclogenesis to go. But if these cases that are marginal humidity environments where it barely makes it in the current climate, it doesn't make it in the future climate. And so, there could be a real basin dependence to this, because I think in the Atlantic basin, you have a lot more sort of moisture-limited tropical cyclogenesis events, say, compared to the West Pac or something where there's no Saharan air layer upstream, feeding in. But anyway, so to summarize kind of this previous work, most of this, this isn't really exactly my area. I had 2 really good grad students who worked in there, Kevin Hill and Megan Mallard. And what we found, I think, corroborates what other people have found, and that is with warming, the strongest get stronger, and that's really just due to the fact that it rains harder when there's more vapor. But the TC genesis decreases, but it's the weaklings that get picked off in the future. And that's because of this increase, even with constant relative humidity, just because you're increasing the saturation deficit, it just means a little more time to genesis and a little more convection is needed to moisten the environment enough to get it to go. So, that's kind of the backdrop here. And then now the next part is Hurricane Sandy. So if anyone has any questions, I guess I'll take a quick question now if anyone has one, and then we'll move on to part 2.
when you make the changes, did you change the wind fields, or is only you didn't change the wind field?
That's an excellent question because, in fact, I have a slide that will let me delay my answer to that question. But that's something that I think every time I do this talk, someone asks, and it's an excellent question. And so I submitted this paper, and one of the reviewers said, well, "What about the wind field?" And so we have to address that. And I think I have a good answer to that question, but let me hold that until the end. Because the answer is no, we don't change the wind field, but we went back and did some where we did change it to test to see how much it mattered. Okay, well, let me proceed then. So when Hurricane Sandy happened, some of the local TV stations called me up, and they didn't want to talk about the storm. They wanted to talk about climate change. And, they just said, this is it, climate change is upon us, and, if it weren't for climate change, this wouldn't have happened. And, there's a lot of interesting discussion. And, you can see it in the headlines, you can see it in the media, and in the literature. So, Francis and Vavris, they said, look, with the polar amplification, Rossby waves move more slowly, it's easier to get blocks. Barnes et al. Came out with a counter to that, saying, actually, if you look at the GCMs, there's a decrease in the frequency of the type of steering flow that led to Sandy in the future. So there's a lot of controversy about this, really interesting. And so the question that we can answer with our pseudo-global warming technique is, did the thermodynamic changes that have taken place to date make much of a difference for Sandy? Or if the synoptic pattern that accompanied Sandy were to take place in the future with future warming, how would the event have changed? So, we have a limitation. We can't answer questions relating to, the frequency of patterns like this, but we can say, did the thermodynamic changes that took place, were they sufficient to make an appreciable difference in the storm? So, to remind you, so I lived here. There was this is the 250 millibar height analysis overlain on the water vapor image from just around the time that Sandy was making landfall in southern New Jersey on 0Z October 30th. So beautiful, but very destructive storm. A lot of interesting features interacting with synoptic flow. It's a nice paper that Tom Galarno et al. With people here wrote that showed that the maintenance or re-intensification that Sandy experienced before landfall was actually related to sort of baroclinic processes, frontal type processes, which would justify labeling it as extratropical or post-tropical prior to landfall, which is, there's a lot of implications, in terms of insurance payout and whatnot to have it not be a hurricane. But, there's a lot of, in fact, I wrote this paper about Sandy and I submitted it, and I think there's 3 or 4 other Sandy papers that have come out since I submitted it that I wasn't aware of at the time I submitted it. So I've worked those references in, but there's so many papers being written about this case because it's such a fascinating case. I think I was grousing about that to Tom earlier. But anyway, there is this, you can see the outflow. You can see sort of the limiting streamlines in the water vapor image. You can see the outflow and how it's really helping to build up this ridge to the north, this blocking ridge. And then there's a wave breaking event, so you have a upper level cyclone to the south, so it's like your old Hot Wheels supercharger just forcing the storm right into the coast. And this shows the height anomalies, and then the Christmas tree looking, Christmas color PV. This is the low level PV field, so that's Sandy. And you can see the upper level height anomalies that accompany this evolution, driving the storm on its unusual track. There was a paper by Sobel and collaborators that said that a landfall angle on the Jersey shore is like a 1 in 714 year event if you look at all the data from past tropical cyclone tracks. So an unusual synoptic setup led to this. And we could say, well, how would this be affected by climate warming? Well, maybe with warming you get more latent heat release and that builds this ridge more, and that drives the storm more strongly westward. Or you could say, with future warming, the upper jet strengthens, and that would tend to push it more eastward. Or you could say maybe there's more diabatic erosion of the low to the south. That might also give it a more eastward track. It's not clear. There's offsetting processes. One thing we did with WRF, I hope you can see this okay. One of the first things I did was I ran it full physics, and I got a good forecast. I was very happy. 5-day forecast initialized with the European Center. And then I turned off latent heating and ran it again. And what this shows is the sea level pressure from the full physics run, but the wind vectors are the difference between the full physics and the no latent heating run. And what it shows you is a huge anticyclone. So here's your upper level outflow ridge that's really attributable to the storm itself. So, and this has been shown before, but you can't negate the outflow from the storm in steering itself to some extent, even though this is higher levels, maybe above the steering level of the storm. But certainly you can quantify the diabatic contribution to that downstream ridge with an experiment like this. Yes, Morris?
What are the magnitudes of those vectors?
Oh, that's a really good, I don't have a scale vector on there. And I can't blame IDV, but I should have one. I think they're on the order of 5 or 10 meters per second. I can find that out for you. That's a good question. Shame on me for not having a scale reference on there. It's a good call. But it was a significant. It was pretty strong flow. I think it was on the order of, the strongest part's probably on the order of 10 meters per second. So again, we have offsetting processes, and so several things that might suggest a stronger storm, a few things that might suggest a weaker storm, and we have things that could potentially, conceivably shift the track westward or eastward that I mentioned. And so you can't guess which of these processes are the more important, but fortunately we have the WRF model, and we have credible current day experiments that we can use as a baseline and then see what the changes were. So I'll try to, I don't even want to think about how many simulations I've run of this case because it's depressing, but I really do enjoy, you can tell I enjoy running the model on this case. So what I finally settled on, and I even tried some of the more recent versions because one of the reviewers on my paper said, it all comes down, for the coarser grid spacing, it all comes down to the convective scheme. If you run the TDC convective scheme, you get it right no matter what. And if you run the simplified Arakawa-Schubert or some other scheme, then you have a worse time. And so to use the TDC scheme, of course, I had to use the more recent versions and the ones that adjust momentum. So thanks to the WRF people for putting that in, because that could also, when the convective schemes adjust the momentum, that can have a lot to do with both the intensity and the track of the hurricanes. But anyway, so it's been a long, I've been running a lot of model runs, but in fact, here's the table that shows some of the different runs that we did. I won't get bogged down in here, but what we did for our control run, it started off, it had to catch up, but sort of from 18 hours on, with the exception of this little divot here, so the black dots are the best track. The slope of the best track line, in general terms, is fairly similar to the ensemble mean. It's a physics ensemble. It's not perfect. And fortuitously, the observed central pressure at landfall was 940, which is just what the ensemble mean was a little bit. The ensemble was a little bit slow, but for me, I was pretty satisfied with this, considering I wasn't nudging. This is a 5-day forecast, and so I was pretty happy with it. I mean, it's not perfect. And here's the ensemble. The best track swung a little farther east down in here, but again, fortuitously probably made landfall within 15 kilometers of the observed location. So I was pretty satisfied with that. Never going to get it perfect, but that's the current day. Now, if this had happened in 1880, what would happen? So, it's hard to find a good data set to really say, well, what has changed since 1880 using, looking at the temperature, say the 2-meter temperature, 950 specific humidity. We did this calculation using the 20th century historical runs from the CMIP-3 GCMs, and we took the difference between the 1880s and 2010s. And we applied those changes to the European Center analyses, reran the case. You could use maybe the 20th century reanalysis or some other observational data source to check this. Would be a good idea. But this is what we did. It'd be a little cooler, a little less moisture in the 1880s, maybe less diabatic ridging to the north. Maybe the storm will go out to sea, which would have caused an uproar. But as you can see, that was not the case. And in fact, the historical version of Sandy took more of an aim at the DC area. There was only one ensemble member that was as far north as the observed location. So the whole ensemble shifted south. And I've done this with all different kinds of model configurations, and this seems to be really robust. But the past ensemble mean track was consistently south, but not by a huge distance. And then the intensity, so here's again that current one. The current one's the blue line here. The historical Sandy was the green line. So it was a little weaker, maybe 3 millibars weaker ensemble mean. But when you calculate, there's a lot of ensemble spread. So when we did I did a significance test and it failed. It wasn't, the difference wasn't significant. So, the track shift was very consistent. There is a tendency for weakening, but it didn't prove to be statistically significant the way we did this. So what about the year 2100 version of Sandy? So we did the same type of thing using a subset of the GCMs and the A2 emission scenario, which is probably the most aggressive, but also perhaps the most realistic. And we did the same thing, the same physics ensemble. And again, there's compensating processes. Here's the change field. Now, there's something I should point out about this. You notice how the temperature change field is nice and uniform, which means that you're not changing the thermal wind drastically, and maybe you don't need to adjust the winds. But the moisture changes, the way we didn't apply the GCM moisture changes, we instead assumed constant relative humidity, which means that you get the most vapor increase where you're in the warm sector, where you have warmer air. And the reason we did it that way is because I think this is much more realistic of what it would look like. If you just tack on a uniform humidity change, you're going to be changing the relative humidity in places where it's cooler and reducing it where it's warmer. But if you keep the relative humidity constant, then this is the vapor change field you get. And when you run the future Sandy, it takes aim at New York City, eastern Long Island, and the track shifts decidedly, makes landfall decidedly farther north. And why is that? Well, if you look at this is a complicated figure, as the reviewers let me know when I tried to put it in my paper. But because the upper jet increases more, so what this shows is 300 millibar geopotential height, and so I put the contours on there for reference, but you can forget about those. That's not the focus. But the yellow shaded areas are where you get less of a height increase in the future, and then the dark shaded areas are where you get more of a height increase in the future, and then the arrows are the vector difference in the wind. And again, I need a scale on here. I have another figure that shows the values though, so I know these are about 3 meters per second, 3 or 4 meters per second faster westerly in the future. And what that means is during the time, and this is time averaged over the period of time when the storm was moving in this area. So, and so it's a 36-hour time average. And what it shows is you get increased westerly steering flow across the track of Sandy when it was in that location. And so that's why I ended up making landfall farther north. This shows a loop, again, a complicated figure, past, current, and future, color-coded for your convenience. The upper level PV, which is the 200 to 300 millibar PV, is shown in the shading. And the low level PV is the black contours. And then the wind field above a certain value, I think 50 or 60 knots is also included. But what you can see is that the upper trough to the south, it's there. In fact, I have a still here because that's you get dizzy trying to follow that. But if you look, this is hour 84, so 12Z on the 29th. Or maybe that's 12Z on the 30th. But this trough is very similar in strength in each of these three, but its location, the axis of the larger PV is shifted northward in the future relative to the past. And so that's, I think, consistent with the whole, a whole shift of the pattern. It's more progressive, and you have stronger westerlies, and so the storm deviates farther eastward and then comes back and makes landfall. Now, as far as the intensity goes, it's, some of these future ensemble members get down to, the 9 teens, so it'd be making landfall with a sub 920 pressure in some of these runs. But the ensemble mean was in the upper 920s. So there's significant increase in future intensity beyond the current or the past. And that was statistically significant. I didn't test for 99%, but it was significant at 95%. So the future Sandy was much stronger. And why was it stronger? Well, it's consistent with, in fact, if you look at when it deviated, I should have pointed this out. So when the future Sandy got the jump on the current and past, it was early on. It was, in the first few hours, really, of the simulation. And then after that, it was, the deepening rate was a bit stronger, but it was just kind of steady. And if you look at the precipitation, the future run had heavier precipitation early in the model forecast, right at the time when the strength jumped out ahead. And if you look at the PV tower, past, current, and future, you can see that the future PV is larger, covering a larger area, which is consistent with greater intensity as well.
Do they all have the same sea surface temperature?
No, the sea surface temperature was changed in the same way as we used the GCMs to include the sea surface temperature as well. So one of the reviewers said, well, by the time you initialize, the variability was winding down. You should try initializing 48 hours earlier. So I did some runs now using WRF 3.6 with a Thermodynamic convective scheme. And, I got pretty much the same type of result. Current is blue, future is red. But even this is now a 7-day forecast, initialized with the European Center. And with the Thermodynamic scheme, the observed, it's amazing. This is this paper by Nick Bassel in GRL that found that it was really, the Thermodynamic CP scheme could do no wrong with the Sandy event. So, and I found that with WRF, using it in WRF as well. But when I gave this talk, a related talk at the Cyclone Workshop, Fucheng Zhang was there, and he said, well, but you know what, given what you've told us about warming and tropical cyclogenesis, maybe Sandy wouldn't have even happened in the future. Maybe it would have never even gotten started in the first place. And I said, that's a good point. So we need to go back and look at the really early evolution to see maybe we would have never come to this point. But anyway, as far as the part of the evolution once it had formed, it really seems that there's a consistent signal from the warming. We also, someone said, well, instead of using the GCM mean, why don't you apply the changes from the individual GCMs? And that also gives you a very similar result. There's a little bit more spread in the intensity and in the track, but the bottom line message, the ensemble mean hardly changes at all, either for track or for intensity when you use individual GCMs. So there's not as much sensitivity to that. So to summarize, I should see how I'm doing for time. The thermodynamic changes do make a difference, and we can use this technique to say, well, how much and what type of change do we get? So, the past version of Sandy really wasn't significantly different from the current one. There was a tendency for a more southward track and a more southerly landfall location, and slightly weaker, maybe 3 millibars in the ensemble mean. But that suggests that thermodynamic change to date had a modest direct influence on Sandy's track and intensity if that same pattern had happened in the 1880s from that point on. But, of course, there's lots of other things that we're not addressing here. We're not looking at the frequency question for this type of pattern, which is arguably more important. And also things like sea level rise and the amount of coastal development, which is really virgin since the 1880s, that I'm sure makes it a much more expensive and damaging storm now. The future version, it shifts significantly to the north and east and is significantly stronger. We did use the A2 emission scenario. We should probably use RCP 4.5 and 8.5. You always get just sort of different amounts of the same answer, but for this scenario anyway, the changes were definitely statistically significant. And we got a stronger storm, heavier rainfall, more of a cyclonic PV tower. The diabatic, when I first did this, I thought, well, the warming is making that ridge to the north stronger, and that's going to control the track. That turned out to be wrong. That wasn't the dominant influence at all. So I went in with a hypothesis that I could reject after doing all these experiments. And again, there's a lot of other factors. There's a lot of other facets to this. I was just trying to look at this one aspect of it because I think that's something you can do pretty cleanly without having to make too many terrible assumptions, maybe just a few. So there's a lot more that would be nice to do. I'd like to use the 20th century reanalysis to recompute the past. And I'd also like to look more into the dynamics of it. Tom's nice paper shows this baroclinic mechanism, but the future track, was going at a different angle to the Gulf Stream wall, and so that it would be interesting to see how that appeared in the future simulations. And I would like, so Fuqing gave me all of his ensemble perturbations for the real-time systems, so I'm going to try to make the time to go back and rerun some of the really early simulations and see if it doesn't even form in the future climate. So my paper's in review. Wish me luck. I just sent in the revision, so hopefully we can get it through. But I think I've tested everything every way that I can, and I'll live with the assumptions that go into the technique. And I'll like to thank Bill and Jamie for the invitation and hosting me and inviting me here to speak. And I have to mention my former students, Kevin Hill and Megan Mallard, who did a lot of the work that I showed at the first part of the presentation. And then people that have given me excellent feedback, including Tom on the paper, my BAM submission, and the funding agencies. And with that, I'll take any questions and feedback that you guys have.
Since we're doing the webcast, so I appreciate it if you could use the microphone to ask questions.
There's one over here, Bill.
Yeah, I was wondering how you applied this constant relative humidity criterion. Do you do it for the whole troposphere? And if so, how do you do it at temperatures below freezing?
Well, for this case, I mean, in the far northwest part, there was some areas that were below freezing, but most of the domain was safely above freezing. At higher altitudes, we still assumed assumed the same relative humidity, so we didn't account for ice processes. It's true, the freezing level is higher, so there is a zone in there where that could be problematic, but we didn't see any, if we look at the cloud water fields or anything like that, we didn't see anything strange looking that resulted from that. So we've tried this both ways. We actually looked at this a lot with the tropical work we were doing, where we looked at using the GCM humidity changes and applying those. And the problem with that is that then you get too homogeneous of a change field. So then you're moistening it too much in the cold air and not enough in the warm air. So even though this technique may have some limitations, I think you get something that fits with the synoptic pattern more reasonably. But yeah, it's a good question.
So I'm wondering about, like, to add another set of simulations or thought of simulations. What would happen if you did run it like a convective permitting sort of scale? Because you saw some sensitivity when you had the TITCA scheme versus using the simple Arakawa scheme. Do you think that that would sort of change the trajectory? I mean, you had a great forecast given the TITCA scheme, but would it change the sensitivity related to warming? Do you believe that that would still look the same, or is there any reason to believe that it wouldn't look the same?
Yeah, and I have done convection permitting or convection allowing simulations. In fact, the 6 kilometer simulations, most of those I ran without a convective scheme. And I look at Morris thinking, okay, yeah, it wasn't 4 kilometers or less, but it did really well. And I did 2 kilometer simulations as well. The thing that this paper by Nick Bassel showed is that even with really coarse resolution in the TITCA scheme, it nailed the track. It really wasn't very resolution sensitive. So, for the others, I've done other types of studies like this, like the Tennessee flooding from early May 2010. And that also I did a lot of 2 and 6 kilometer simulations with, and the results were pretty consistent. The thing that's nice about the convection allowing runs is then you can look at things like how the updraft strength changes, which you really can't do with a convective scheme on. And what you find is that with more CAPE, you get stronger updrafts in the future. But I think that was what was going on here too in the higher resolution runs. But yeah, it's a good question. See this one.
My question is that how did you calculate the anomaly against?
Like the height anomaly that I showed?
Height anomaly, PV anomaly, something like that.
Yeah, that's another astute question, because what I had to do there is I rescaled the anomaly. So I used the zonal mean, a GFS zonal mean, but for the past and for the future, I applied the mean height change. So the base state that I subtracted off was different by a constant amount for the past and the future. So I calculated that to account for that, to try to get a meaningful anomaly. But that was difficult. I tried that a few different ways before I settled on that as being the most meaningful way to do it. But I did account for the mean changes in the geopotential.
So how much different is the past versus current versus the future versus current? Is the future versus current about 3 times the temperature different? Because the intensity was a lot more different, but it's not. It could be related to proportional to the temperature difference.
Yeah, I think that's correct. I mean, the changes past to present are really pretty modest, especially in that area. Whereas for the future, it was a much more drastic change, and that's partly because I used the A2 emission scenario, which is on the high end, but that's probably the one that's the most realistic to use from the SRES scenarios. So, but yeah, I think it scales kind of linearly. So I think that's correct.
In comparing the tracks between the future run and the earlier runs, how much of the departure in the track do you think is due to differences in the upstream trough versus differences in the vertical structure of the vortex itself, whereas in the future runs it's much more intense, so maybe it's sensitive to a different steering layer flow?
Yeah, that's a great point. And I haven't done a careful analysis of the steering. So at this point I can sort of hand wave and say that the dominant effect seems to be the fact that you have a stronger westerly jet, and that leads to more progressive synoptic wave pattern. So that kind of the trough that was to the northwest of Sandy was more progressive, and so you ended up with less height rise there. The complicated figure that had the yellow and the dark red, that westerly that you saw there seems to be the dominant effect. And so I would say, the trough to the southwest of Sandy and the ridge to the north had less to do with the change than just the general stronger background westerlies and the more progressive wave pattern. But I haven't done a real careful steering, looking at the advection of the PV tower type of analysis yet. But I should do that, because then that's a good point. I mean, it was stronger, so the steering level could potentially be higher up, which might also explain the difference in the track. But I did a back of the envelope, and it looked like the amount of increased westerly across its track was enough to explain the track deviation. But that's a very, very possible outcome, because it got stronger earlier, so that means the steering level could have been higher earlier on.
So you promised to respond to my question about the wind.
Oh yes, let me see. So one of the reviewers was saying, you can't change the temperature and moisture and heights without also changing the wind. And my first answer is always, well, the temperature changes we're imposing are very smooth, and they're averaged over decades, and so there's no drastic changes in the thermal wind. But the moisture changes do have sharper gradients, and the geopotential is built from the virtual temperature, not from the temperature. So those moisture gradients could lead to height differences. So I said, I better go back. And fortunately, WRF, one of the other wonderful tools that it has is this digital filter initialization. So I went and ran with that, and for the past, the track was virtually identical. For the future, the DFI track was, at least for part of the run, was actually slightly further east. And you could argue that that may be because when you adjust the wind fields at the start of the model run, then that westerly is there a little earlier on. So that might have actually kicked it eastward. But the change is really pretty small. So I was relieved when I did this run, because then I had something I could respond to the reviewer with that was more than kind of a hand waving. But that's another reason I like using this model, is it has so many nice tools built in that you can do this and balance the wind fields at the initial time and see that you still get a similar result. So, are you satisfied? Maybe you were that
satisfied.
Reviewer.
I'm not a reviewer.
Okay.
Okay. Any more questions for Gary? Gary will be here tomorrow morning through around noon, and his office is located on the first floor of FL3, near the southeast corner. So please, we'll welcome you to visit him if you have. He will be available, I guess, between 10 and 12 if you're interested in talking to him more. Let's thanks Gary again for his excellent talk.